Alright, silly people, here's the situation. Uh, we are just proving uh, this relation for the total angular momentum operator j squared is equal to this stuff um, using the definition of the ladder operators and the general commutation relation for angular momentum operators. Uh, and then the second part of this problem is to find C minus, which is the constant that appears in this equation. It's kind of an eigenvector, but kind of not. And we're supposed to be using, to do that, just the general equations for the angular momentum eigenvalues, which I've written there. So let's just get to it. How do we make j squared look like that stuff that I wrote up there? Well, j squared um, is just jx squared plus jy squared plus jz squared. It's a dot product of two different angular momentum vectors. Um, so let's actually investigate the quantity j plus times j minus. Using the definition of the ladder operators, we know that this is just jx plus ijy times jx minus ijy. And when we expand that, we have jx squared minus ijxjy plus I times jyjx minus I squared jy squared, which simplifies to jx squared plus jy squared. And we'll factor out an I. Jyjx minus jxjy. So that stuff inside the parentheses there is a commutator. So we can write this now as jyjx. Yeah, it's the commutator of jy and jx. All right. So what is that commutator? Using the general formula for commutations of angular momentum, jyjx will be ih bar, Levi-Civita symbol. You're going to have 2, 1, 3, which is not a cyclic permutation of the Levi-Civita symbol, so you'll have a minus sign, jz. Putting that back into our definition of j plus j minus, you'll have jx squared plus jy squared minus I squared h bar jz. And then if you square the I, it's all plus on this side. So let's just use this to get a expression for jx squared and jy squared and plug it in to our j squared equation, which now is going to read j plus j minus minus h bar jz plus jz squared. Done. That's how you do that proof. Next bit is to find what C minus is. So how are we going to do that? We're just going to first move everything that isn't j plus j minus to the left-hand side. So the total angular momentum squared minus jz squared plus h bar jz is equal to j plus j minus. And then we're pretty much just going to find expectation values for these guys. multiplying each of them on the left and right sides by bra jm and ket jm respectively. Equals jm, j plus, j minus, jm. So we do actually have values for each of these expectation values. So that's going to be j plus 1 h bar squared. This is going to be minus h bar squared m squared, and that's going to be h bar squared m. Okay. On the on the right hand side, we're going to make use of the fact that from the definition of the ladder operators that j plus is equal to the dagger of j minus, and rewrite this now j minus dagger j minus times jm. Okay. I'm going to factor the left hand side. I have h bar squared. The polynomial will be j plus m, j minus m plus 1 times j plus m. Is that right? You still have the j squared. You have minus mj, you have plus mj. You have j, you have m, you have minus m squared. Yeah, looks good. On the left hand side, now you just have, you're going to end up with c minus squared whenever you left operate jm and right operate jm, you just get that stuff. And then the other stuff, I guess I'll write this out. Jm minus 1 and times jm minus 1, that's equal to 1. So equal 1. Then you just take the square root of both sides, and you get this stuff. And now we've found values for c minus.